Let's discuss the new mathematics that will be based on these two new entities that we introduced. I forgot to mention last time, so let's add that additional qualification. It's an important qualification. This vector space is a complex. So it is more general than being a real vector space. And the reason why it should be a vector is not that clear at this level. If I had to use this analogy with the light polarization, not photon, let's call them, then, for example, to get the, for example, when we are having this as a basis, there is a particular state corresponding to spin up, alignment of the spin along the direction, the external direction, or down. This is a basis, so anything can be expressed. That's the definition of a vector space. In terms of the spaces, or the SX spaces is an alternative basis, which is obviously orthonormal and complete. Any vector, arbitrary vector, can be again expressed in terms of this. Or eventually, as there is no difference between X and Y and Z directions, because we are free to orientate our external reference direction in along any axis. So we could in principle have a SY basis. That is the eventually I will call them the eigenvectors of this Y component of the spin. Anyway, we don't know it yet. But if we have to really use a real vector space with real coefficients and all that, we'll have difficulty in accommodating a third entity. But that's not a very good argument. It's only a plausible argument. We will fill in those gaps eventually as we move along in the direction. But this complexity is very important, okay? So let me start discussing the properties of this new space, which is a complex vector space associated with the quantum states now. So different, you notice that so different than the classical definition of state in terms of the dynamical variables. Now we said the dynamical variables are represented by the Hermitian linear operators. Well, these go by the name of observables. If we were talking about abstract, any type of more general operators, we would be allowed to call them the operators. But our operators are not of most general type. Well, that's a subset. The subset is chopping off the larger class into a linear class. You'll see the reason for that. And furthermore, the Hermitian, we'll see what the features of the Hermitian operators eventually in a few moments. So these type of operators with these two qualifications are called observables because they are related to the observed or measured quantities in the classical physics, like the position and the momentum, or the energy, angular momentum, the stuff like that. So that's the name. All right. So we have a complex vector space. If it is, in principle, for many physical systems, it's finite dimension, like the spin 1/2 or spin 1 or any spin systems. They're finite. Sometimes they may be infinite. Therefore, in the case of infinite dimensional vector spaces, we will use a new name. You have to always remember that those infinite dimensional spaces are called Hilbert spaces. That we will come across to those infinite dimensional vector spaces when we are going to the concept, when we move into the concept of wave function, which are coordinates of the abstract vectors in the same position eigenvector basis or momentum eigenvector basis. Anyway, they are the coordinates, these functions, as they are labeled by a continuous variable. Obviously, continuous variable is innumerably infinite, so they are really infinite dimensional. But for the time being, let's proceed with these finite dimensional vector spaces. So they have all the nice features which will be easy to illustrate concerning the theorems that we will be talking about. These observables, or the linear Hermitian operators, eventually I will elaborate further, they also live in the same vector space. So the vector space we have, complex vector space. In it has these vectors, state vectors, and they have the observables. There are observables in it. So it is a bag of mathematical structures, right? There are the vectors, which are in principle complex vectors. There are observable, those operators, and the operators will have further entities associated with them. But let's see, as they live in the same vector space, of course, what we have to decide is, we define the state vectors with alpha. Certain books use psi, but the textbook we are using is denoting it with the first letters of the alphabet, alpha, beta, gamma. So I'm sticking to this notation. And the observables we use, for the observables we use the notation A. If it was general operators, we will be using X. But for the observables, that is those associated with the dynamical variables in a distant manner, though, they will use the notation A. So obviously these operators should be acting on those states. We define this action as such. These are the linear operators, and they are the vectors defined in this manner. In principle, this is a general different vector, really. When you take an observable from this space and act on an arbitrarily chosen state vector, then you get another state. In principle, different than a constant times alpha. Well, this, however, is not meaningless. This right-hand side is a meaning. If it is equal to, if when you have an A, the observable acting on a state vectors of that sort, if it gives you the state vector times a constant, then that particular state is called an eigenstate. So that's the definition of an eigenstate. In general, you get something different than that. It's not parallel to it in that vector space. But when it is so, a constant times alpha, then it goes by the name of eigenstate or eigenket, using Dirac's version. He calls it in short ket, eigenstate or eigenket. So we will then, in that case, we will introduce a different notation. We will say A and use the same small head letters. A, capital A is the operator, and small letter A are for the eigenvalues and the eigenkets. Nice notation. The book uses primes, and I don't like the primes. I would like to label them by discrete indices I, which really I runs from, say, from 1 to n, that capital N will be the dimension of this space, spanned by these eigenkets. So these are eigenvalues. And these are eigenkets. Or eigenvectors, if you want. So, as I said, in certain places you may see primes used for labeling, but it's a very cumbersome notation, right? Single prime, double prime, triple prime. So let's use this index, which is suggestive, saying that it's a discrete spectrum, finite dimensional space, but doesn't matter. We can immediately generalize it to infinite dimension. So eigenkets and eigenvalues are defined as such. So now examples are, in the spin 1/2 case, let me remind you that examples again. For example, we say, example again from the spin 1/2 system, we have the SZ, the Z component of the spin observable, spin operator if you want, plus minus Z is defined. This is the result of this Stengel experiment, right? It is when it is parallel to the external magnetic field direction, its magnitude is h power over 2. That's the reason why we call it spin 1/2, plus a half and minus a half, right? I use this particular notation, plus, minus, and sub Z, indicating that it is associated with the Z component of the spin. And there are other people using different notation, more cumbersome. But anyway, I prefer this shorthand notation as more aesthetic. Or if you want, as we have illustrated in the particular experiments depicted in the board, you can think of the eigenvectors of this X component of the spin. Nothing is particular about the direction, so it will have, again, either a parallel or anti-parallel direction in that new direction, which is called the X direction. So these are the eigenvectors of the Z component or X component of the spin, respectively. Now, that's the example. Now, when you have the eigenvalue problem defined for an observable, and if there are n many of them, I is running from 1 to n, then an arbitrary state in this vector space, an arbitrary state, alpha, can be written as a superposition of, in terms of these eigenvectors. I is running from 1 to n. That one qualification important, as I said, we are talking about the complex vector space. These coefficients are complex. That's a very crucial information. You know that complex numbers are the doublet of real numbers, therefore this space is twice as large as a real space, so it contains more information. It is not only going from a symbolically real to a complex, there is more information in it being complex. Well, this is a very important statement. This is the famous expansion postulate of the quantum theory, and it's at the heart of the so-called Copenhagen interpretation. When you write this simple and naive expression, together with some further additional physical inputs, but that's the heart of the Copenhagen interpretation, expansion postulate. If an arbitrary state can be expressed in terms of the eigenvectors of an observable picked from the space itself, that both sides contain the same information. If it is a state, arbitrary state, it must mean it should contain all the information as complete as possible about the system, right? That's the definition of a state. You should be in principle able to answer all the questions concerning the state of the system. That's the state. That it can be written as such is a beautiful and very powerful assumption or postulate or axiom. You can use any argument you like. That's the Copenhagen interpretation. Well, of course, when we are making such a strong assertion, there is a very important question to be posed and answered. Is this a unique expansion? So let's pose the question and let's proceed. So I think I should get rid of this. It was so educative to have this around. Let's get rid of this. So whether that expansion is unique or not, we'll answer that later. We don't know yet. Let's take it as an assumption for the time being. And as we will have more tools developed along the way concerning the nature of the vector space and the operators and all those things, we will be in a position to answer that question. And the answer will be yes, of course. That is, if it is at the heart of the Copenhagen interpretation, that must be unique expansion, which will mean the completeness of the basis vector. We don't know. Well, let's assume it and let's proceed. Now we have the cat space. Cat is the language of Mr. Dirac, which are having the elements alpha denoted as such. And we introduce another space dual to a bra space. And they are represented, the vectors of that new space, bra vector space, is denoted by these with the symbol. And this is a dual correspondence, dual correspondence. Between those two spaces. And we have the collection of basis vectors. We choose the basis vectors to be the eigenvectors of an observable. And there will be a dual basis denoted by these dual, the bra basis vectors. And the correspondence is valid for this superposition of two cats, alpha plus beta, and it has the corresponding ones in the bra space. Similarly, you can multiply a cat with a complex number, and that's really sort of the new feature which makes its peculiarities more manifest. The corresponding bra in the dual space is obtained by taking the conjugate of the C, or we can generalize this and write this as superposition of two arbitrary cats, and its correspondence, dual correspondent in the bra space is with denoted as such. Okay, that is the relationship between the cat space and the bra space. This is a complex vector space in its own right. That's another complex space on their own right. So we have to now introduce structures. There are several structures that we are going to introduce. The first one is the inner product of a bra and cat. Okay. Well, it is defined in the following manner: a bra and a cat. The definition is symbolically as such. That is, in general, a complex number. A complex number in general. So what are the properties of this so-called inner product? That's a new structure. For the time being, it is just a definition, right? I said I took one bra from the bra space and one cat from the cat space and associated them with them a complex number defined in this way. That's the notation. So there are the property of the inner product. Property 1. Well, if you want, you can say postulate 1 associated with the. You are defining your inner product through these properties or postulates. That is, beta alpha is alpha beta complex conjugate. If you interchange the bras and cats from the bra space and the cat space, then the complex number you associate with this new structure is conjugated. That's postulate 1. Space in here, that is what corresponds to, right? The inner product of two vectors is defined as b dot a, and this is actually this what corresponds to this one. What about alpha beta? The analog again is similarly, these are ordinary three real vectors in the ordinary tree space. Notice that although they are analogous, one thing which makes it, which sort of puts a distinction from the ordinary tree space, real tree space, is that although these are the same, right? And this is not the same. So you pay attention to the fact that it's a property of the complexity of the space, that alpha beta and beta alpha bracket are not the same. Okay, which it follows from here that I can write it as a lemma or whatever as a result if you want. Alpha is real. If you take the inner product of a cat with itself, which you define as such alpha, it's real. The proof is immediately obvious from this theorem. If I take beta to be the same as alpha, that's what used to be beta first. Alpha, that's the beta. You just obviously it follows from here automatically that it's this self-conjugate, right? Alpha is the same as alpha star. It is nice, but let me list the property 2 to come up with some physical implications. The property 2 is what? Or postulate 2 if you want, property 2. I hesitate to use the postulate, it's too strong because I reserve that terminology for the postulates of the formal structure of the quantum theory. Therefore, I introduce the definition, I list the properties which I impose to define that inner product structure. The property 2 is alpha is non-negative. You impose this. And when the equality holds, well, that special case holds when the vector is itself null. If so, then alpha is 0, right? For the equality case. Null. Now let's introduce a definition. Orthogonality of cats. Here is the definition. If the inner product of alpha and beta, two cats, you have two cats, you take them, by the way, notice that it's, if you are not that familiar with the vector spaces or complex vector spaces language, then you may say, well, what are you talking about? It is the inner product two cats, but involves the bra. When you take the inner product of two alpha and beta cats, you go to the bra space and take the bra dual of the alpha cat, and you associate this bra and this cat, then make an inner product. If the result of this is 0, then you say alpha and beta cats are orthogonal. Okay, that's the meaning of this mathematical relationship. Of course, this means beta alpha, which is alpha beta star. This is a complex number. Being 0 means both of its components, real and complex, imaginary components are 0. Therefore, it is a complex number is 0, its conjugate is 0. Therefore, its conjugate is equal to beta alpha. So it is 0. It means that in both ways. Alpha beta or beta alpha is equal to 0, meaning that both of them are orthogonal, two ways relationship. Let's introduce another definition. Normalized cat. I define this, start from the given arbitrary ket, go to what I call a twiddle, put a twiddle on top of it. I call it a normalized ket by dividing it with a number. This is the original alpha, and I divide it by alpha and alpha. Well, demonstration is 10 seconds demonstration. You take the inner product of these two, take the inner product of it with itself. Then what you get is this square root factor squared times alpha and alpha. Well, that thing is 1 over alpha alpha. Cancels and you get 1. It is indeed normalized in this manner, right? So what is the name? This name then is alpha. Alpha is called the norm of alpha vector. To get the norm, you take the inner product of it with itself and take the square root. It is the norm. What is the analogy with the ordinary tree space? Analogy is, burası iyi değil, şuraya yazacağım. You remember this, right? You go to the ordinary tree vector space. That is how you define the norm of a vector. You take the v squared and take the square root. That is the norm. And it's exactly the same as that in this new abstract space of ours. Now, the important claim is that physical states are represented by normalized kets. As I have defined the norm, I can now really introduce this concept. We said that a physical state is represented by a vector in a complex vector space. Okay, and the physical ingredient was the physical alternatives in an experiment define the dimension and the etc. Those measured quantities sort of enabled you to introduce the basis vectors. We are going step by step. But now we say physical states are really defined by the normalized kets. And I will elaborate on it now. Physical states. Physical, two states, of course. Normalized kets. Well, this is preparing myself towards the probabilistic interpretation of quantum theory, but important things which enabled me to go to that verdict is that the norms are non-negative, or positive definitive if you want, except the very special case of null vectors. And the completeness or uniqueness of the expansion postulate with the complex coefficients. That's it. These two is preparing myself towards the probabilistic interpretation. That's the reason why I say physical states should be normalized kets. Well, let me not jump forward, because let's go step by step schematically. You know why? Okay, let me borrow from the future, but let's not take it as a proven fact to have a feeling about the statement. We know if there's a particle inside this room, what is the probability of finding it somewhere at that corner or at that corner, at that corner? You define the density and integrate over that small volume in there, and that will give you the probability of finding it in that small volume somewhere in there. Apart from that, question, what is the probability of finding that object, little insect, for instance, fly? Somewhere in here, 100%. We know that it's somewhere in here. It is the sum of all the options in any small volume you think of. Oh, that's good. That's the meaning of normalization of the cats. Why we need normalized cats? In a sense, we have normed cats in the vector space, meaning that we are not really having a vector space. We are having a ray representation of a vector space. Only the norm directions are important. When you go to the geometry of the Hilbert space, to the fiber bundle representation, for instance, this ray is an important distinction from the full vectors. It is a ray, the directions only. But anyway, I haven't proven anything. I'm just preparing yourself for future physical interpretation. Let's now deal with the operators. Further, elaborate on the operators. As I said, the two new shifts in the paradigm from classical to quantum. One is in the definition of the states. We talked a little bit about states. The other is the definition of the dynamical variables. From dynamical variables, we move to the operators, order-dependent mathematical entities. Order dependence comes from the measurement. Measurement is order-dependent set of processes, so entities should be elevated to order-dependent mathematical structures. So we have the operators. So when you are talking about operators, of course, you have to introduce a bit of mathematics about the operators. Okay, this is the title of the subject. For example, how do you say two operators are equal? You may say, does it make sense? Yes, of course, there is a definition of it. X and Y are two operators that we consider. We say X and Y operators are equal if X on an arbitrary state vector is the same as Y on the same arbitrary state vector for arbitrary alpha. You see, that's the definition. Arbitrariness is the most crucial. If it happens to be so for a very specific single vector in that space, of course, that's not valid, that's not acceptable. You pick an arbitrary one, you take your X and Y from that bag, act on the state, and you get a new cat. If these new cats are equal, then these two operators are told to be equal. We are used to the concept of equality of numbers, but not operators, so we have a way of defining the equality in this sense. That's the first property. The second property, an operator is equal to 0 if this is so for an arbitrary. Okay, it's valid. This arbitrary alpha is valid in both theorems. When you take that X and act on an arbitrary state, if you get 0, then you say that operator is null. Now let's define the addition of operators. The first property is addition is commutative. May sound trivial, but these statements are not trivial. Huh? You can add them in any direction. And they're also associative. Associative. quite easy to accept. Now let me define a new class of operator. They are the linear operators. Remember when I said I'm constructing the new entities associated with the dynamical variables of the classical physics, we said they must be linear, and I also added Hermitian, but Hermiticity I will discuss in a few moments. Linearity is an important thing. What is the meaning of linear operators? Linear operators. X is linear if C1 alpha plus C2 beta, you pick two arbitrary cats, alpha and beta, multiply them with arbitrary complex coefficients, then if it is, again, this may sound trivial, but it's not. And you can think on your own, find those particular operators which are not really satisfying this linearity property. Most of the trivial operators you can think of, like derivatives or so on and so forth. Or when you say operators, the first thing which comes to your mind is that they are derivatives, an ordinary operator. But there are other operators, physically meaningful and profound operators, which may not satisfy this property. Now, what about the product of an operator, the action of an operator on a cat, for instance? Let's discuss that. That's the linearity. Action of an operator on a cat, for instance, which is written as X alpha, as we have seen before. We have all these entities, mathematical entities, live in the same complex vector space, the operators and the cats and all that. And of course, they have to act. That's the reason why they are introduced. They have to act on these states. What is their dual? What corresponds to these in the dual space, the bra space? Or one thing, you have the alpha and the alpha, and you have the X alpha, which is another cat, right? Beta. And this is another bra, really. Not the same as alpha. In principle, you act on it by X, you get another cat, and the same, you act on it from. Oh, by the way, notice that I'm paying certain attention to the ordering of the when I'm defining a multiplication rule. There are certain orders, and there are certain orders which are not legal, according to Mr. Dirac's veto. There are legal orders and illegal orders, and these are the only legal orders that we have to stick to. We have to adapt ourselves to. Okay. But the point is that these two, or that two, are not dual correspondents. Alpha cat and alpha bra are dual correspondents, etc. But when you are having a beta defined by X acting on it from the left, and then you have another thing, then you are having X acting from right, and perhaps I should not use this beta because they are not really dual correspondents. These two things are not dual correspondents. What is dual correspondent is defined through the following. X on alpha, the dual correspondence is via this relationship. When you are replacing this cat with the bra, And you have to replace X with something called X dagger acting on that bra from right. That's the dual correspondence. It is so important. It may sound just a notation, but I'm moving towards defining the Hermitian operators and hermiticity, and it will follow from here. Let me define that before we go out for the last break of the today. Okay. This quantity, perhaps I should use a different color to indicate that I'm defining a new thing in here. This quantity is called the Hermitian adjoint, or just adjoint in certain books. Hermitian adjoint of X. So operators also change in nature when you go from ket to dual bra space. If X is equal to X dagger, this is now defines, reduces the size of the set of operators to a smaller set. Only those operators satisfying this property are called Hermitian operators. Obviously, not all operators you can think of will be Hermitian, and only there's a special subset satisfies this. That's the Hermitianity. Now, the multiplication of operators. Let me start that subject after another short break. I promise to come back a little earlier today, but this time before the last session.